So I'm Paul Schmitt, and this was done with colleagues at UC Santa Barbara. So just to give an overview of what an MVNO is, in case some people don't necessarily know, traditional cell networks are known as mobile network operators, or MNOs. And the distinction between the two are that MNOs actually lease or purchase the rights to use spectrum in the countries that they're operating in. So from, say, the governmental bodies like the FCC in the United States. And examples of MNOs in the US would be Verizon, AT&T, T-Mobile, and Sprint. MVNOs are mobile virtual network operators in that they don't actually own the right to use that spectrum. They simply lease the excess capacity that the MNOs have. And basically they ride on at least the radio access layer of the MNO networks. And they're increasingly popular worldwide, particularly because of they often have sort of relaxed contract terms or little to no sort of credit checks compared to traditional MNO networks, so it's easier for people to gain access to such carriers. And so just an example, we've got Verizon here is the MNO, and then we've got the sort of Net 10, Straight Talk, TracFone. There are hundreds of MVNOs that operate on top of the Verizon infrastructure. And the reason we care about this is there was some prior work that showed at the application layer, MVNOs tended to have poor performance in terms of throughput and latency. And so we were sort of curious as to why. We make a distinction in this work between full and light MVNOs. And that really comes down to sort of where they decide to take autonomy from the MNO operators. So as you can see on the bottom, a traditional MNO, basically, they own the entire chain of services. So they own and operate the radio access layer, the routing, the network interconnections, as well as all of the sort of customer-facing pieces of their business. And full MVNOs are this sort of model where they attempt to be a completely separate carrier. And in terms of data networks, they deploy their own core, they deploy their own authentication servers, things like that, HSS, BSS. And on the other end of the spectrum are light MVNOs, and they essentially just ride along on the MNO network. So the MNO is providing them routing and interconnections, and they basically just sell handsets and deal with sort of billing and customers, things like that. So we make that distinction. It'll make more sense as I go through this work. So the research questions that were sort of motivated or that were behind this work were basically, can we identify network reasons behind the quote-unquote poor performance? So why are these MVNO networks typically operating a little bit slower in terms of applications? And then, of course, along with that, are there any sort of areas that are obvious for improvement? And then we were sort of curious about this full and light MVNO thing. Were there any sort of market differences between them? Because it's sort of an interesting way to set up networks now, and we just wanted to see if we could find anything. So the overview of the study is basically we did some active probing. It's a really limited study. It was basically to sort of motivate further work, but we were looking at paths and performance to just popular CDN servers over these MVNO and MNO data networks. So the collection was done in Santa Barbara, California. We had the phones all in a static location, and we didn't move them. And we forced them to use 3G because LTE signal in our location is sort of spotty. It's not universal for all the carriers. So we forced them to use 3G because it's actually pretty good for all of them there. We connected to all of the US MNOs, and we named them A, B, C, and D. And then we used MVNOs on each corresponding to the MNOs, so A1, B1, C1, and D1. Note that B1 is actually a light MVNO, and the others are full MVNOs. And the others, A1, C1, and D1, are actually marketed as the same carrier. So when you go to a store to buy SIM cards, you see many sort of stacks of SIMs and minutes and data top-ups for this same carrier, but the product codes on the SIMs themselves determine which underlying MNO infrastructure you're going to ride on. And for the most part, I would assume that most sort of lay people don't know what the differences are between these. So we thought it might be interesting to sort of compare their performance on the quote-unquote same carrier, depending on the underlying infrastructure. So the data collection was done using Facebook and Instagram servers. And we have this list of 72 Facebook, 36 Instagram. The reason we chose those is they represent around 24% of all mobile data traffic at this point. So we thought it was actually a sort of useful set of servers to connect against. And we used a mix of location-specific and non-location-specific servers. So those that had airport codes built into their URLs, we actually sort of set them aside and knew where those were located. So what we did was we did active probing for 2 weeks in March of 2015. And each phone had a script that ran each hour connecting to all the servers. And we collected basic network metrics like trace routes, RTTs, AS paths, hop counts, et cetera. We also do some geographic work. We analyzed where this traffic was actually moving in space. And we initially started with the IP2 location database. And we ultimately had around 5,000 unique IP addresses that we fed the system. As many of you know, or maybe you don't know, if you've ever used some of these geographic systems or databases, they're actually quite poor typically. Hopefully there's not an IP2 location person in this room. But so what we did was we manually sanity checked all of them using NS lookups and trace routes from looking glass servers. And we basically used common sense where propagation times were impossible, we would move them to the correct location. And incidentally, we ended up overriding around 30% of the IP addresses. And for the most part, what we found was the ones that were very wrong were sort of large, like /16 blocks that were assigned to carriers' corporate headquarters, which I would guess IP2 location doesn't know where to put things, so it just assigns it to the location of the corporate headquarters when we know that there are not 16 million IP addresses that are all in this same location. So initially what we did was basic overall RTTs, and we plotted these CDFs. So these are to non-location specific servers, so things like photos.fbcdn.net. And we see quite a bit of difference, surprisingly, quite a bit of difference between the carriers. And probably the most interesting thing that we saw was the difference between carrier A and A1, the MVNO networks. So the light blue here, carrier A actually is much worse in terms of latency compared to the MVNO network. The median is around 770 milliseconds slower than carrier A1, which is obviously rather considerable. That's going to impact your throughput. So we did measure throughput. It's not in the paper. We measured throughput on these, and we found that A actually outperformed A1. So we believe what's actually happening is our metric traffic isn't being picked up by middle boxes, which are likely present on some of these networks. So middle boxes are going to pick up the client traffic and maybe do some acceleration or proxying for them, whereas sort of trace route traffic isn't going to be picked up by that, and it's going to be just sort of moved along to the actual end servers. So that's sort of our speculation here. We're not really sure, but we saw this sort of odd pattern. This also led us to think sort of, we wanted to know where this traffic was headed in terms of location. And so we took all of these non-location specific requests and mapped each carrier's resolved server locations. And as sort of expected, they all ended up to a handful of 9 or 10 data centers in the United States. And we collected all that information and sort of categorized for each carrier the preferred data centers and the percentage of times that they hit each of the data centers. Now, there are a lot more graphs in the paper, and this is sort of a subset. But what we did here was we actually hit the, on purpose, we hit the different locations, the different data centers. And then the colors on the graphs actually indicate the top 3 preferred data center locations for each of these carriers. So if you're just saying fbcdn.net, where does carrier A send you? Well, 95% of the time it turns out they send you to Dallas from Santa Barbara, whereas carrier A1 is quite a bit different. It still uses Dallas, but the sort of profile or the distribution of latencies that we're seeing were quite different than the underlying MNO. So basically, what we learned here is that location really is sort of highly dependent, or it affects greatly the performance that you end up realizing, which is pretty obvious. But what's curious is why we're actually going to these sort of non-advantageous server sites. So in the case of carrier A, the top three was choosing sort of some of the poorest in terms of latency server sites. Yeah, and carrier A1 has a lot more variance. So we see that basically the MVNO network, this full MVNO, is clearly different than the underlying MNO. Looking at the light MVNO, we see that the distribution of latencies basically mirrors the underlying MNO. So it's kind of what we would expect since they're using the same infrastructure. They're choosing the same, they're preferring the same locations, which are actually geographically closest to us in Santa Barbara, and their profiles are very similar. So comparing the three sort of quote-unquote same carrier, that's the MVNO, we see that they're very, very different from each other. So while they're all different from their MNO underlying networks, they're also different across each other because that underlying network actually affects their performance. So it's like they have three separate cores deployed rather than this one big network. So in terms of customers actually looking to use something like this, they're going to be greatly affected by whichever SIM they happen to choose that day. So at least in terms of depending on where you're coming at this or where you're using this network, it might pay to sort of pay attention to this kind of performance. We also looked at hop counts, and this is sort of, it started to help us understand probably where some of the performance hit is actually happening for these MVNOs. In terms of the full MVNOs, it tended to have sort of path inflation, which we sort of expect, or we anticipate that may be due to maybe they don't have as much sort of or as advantageous of peering, internet peering or internet ingress points, or maybe they have sort of they've bought bulk bandwidth, and so they're entering the internet and they don't have the sort of content nearby them, so they're passing through many different sort of intermediate hops. The light MVNO B and B1, or B1 here, is actually very similar to the main MNO for B. So again, we see that the full MVNOs are clearly a separate network, and they seem to be sort of disadvantageous. So the overall sort of lessons from the network metrics were, it really seems like, at least in terms of RTT performance, that's dependent on server location. Now, server location is impacted by a lot of factors, and cell networks are often sort of viewed as these big black boxes, and there are very few internet ingress points, and the gateways that are used are sort of sparse, and your DNS, as other people have shown in the past, DNS for cellular networks, it operates differently than you would sort of expect coming from a traditional wired network. So there's a lot of factors, and the lack of peering arrangements often sort of causes problems. Some MVNOs we did find had lower RTTs than an MNO, and again, I think that's likely due to, or that's likely a sign of sort of MNOs employing middle boxes to sort of make up some of that difference. We saw there's this path inflation on full MVNOs, and we think, again, they're maybe buying sort of cheap bandwidth. And then lastly, the same MVNOs differ quite a bit based on the underlying networks. So we also looked at geographic paths, and just to sort of explain what happened here, we were connecting, we collected the paths that were used connecting to Los Angeles, which is only about 90 miles away from Santa Barbara, so down here. And we built these graphs, and the arcs actually indicate direction, so you can follow them counterclockwise, so it went that way. And the weight of the arcs showed the sort of percentage of time that those paths were taken. And so we start to see sort of some of the problems that are potentially present in the MVNO networks. With carrier A, 100% of the time it turns out we popped up in Dallas, Texas, which doesn't make a lot of sense. We're guessing that carrier A has some resources in Los Angeles, or at least in San Francisco or something like that. But regardless, we ended up going to Dallas, Texas, and then we would generally make our way back to Los Angeles through Chicago or New York or Washington, D.C. Carrier A1, the MVNO, is all over the place. So we don't really understand why it was bouncing around, but it's sort of just frantic. It's equally choosing paths all over. There aren't any sort of clear patterns that emerge from this. And keep in mind, we're trying to connect to servers 90 miles away. So bouncing around across the country multiple times, just in terms of propagation time, is a bad idea. And potentially you're entering into potential queuing delays at all of these locations, or buffer bloat if that happens to exist in some of these locations. Really, it's a poor sort of use of resources, at least sort of intuitively. When we look at the light MVNO and compare it to the full or the MNO, again we see the light MVNO essentially mimics the underlying carrier. So the takeaway from this is if you've got a really good contract or you see really nice terms for a light MVNO and you don't feel bad about the underlying MNO, from a network perspective, you can really sort of feel free to purchase the light MVNO because you're going to end up with the same network. It's essentially just a rebranded version of the underlying carrier. So again, just the quick lessons there. That's the light MVNO closely resembles the underlying carrier, and the full MVNOs use these very circuitous, less efficient geographic paths. So to return back to the sort of questions that we entered in here, can we identify the sort of reasons behind this poor performance? And it really seems to be destination server location appears to have this dramatic effect on latency. And we think that's due to sort of peering arrangements or lack thereof, internet ingress points, and sort of the DNS choices that these cell carriers make. In terms of improvement, on the whole, MVNOs often have these increased number of hops. Maybe they're purchasing a lower class of bandwidth, or they're passing through multiple sort of subsystems. The full MVNOs use these very strange geographic paths, so we're not really sure on that, why that's happening. Potentially they've got services that are sort of dispersed spatially, and so they need to actually pass through some of these sites. So one of the answers, if that is the case, maybe they should be replicating services in more locations, and overall just basically increasing ingress points and peering arrangements. And some of the CDN companies are starting to deploy CDNs in these mobile network cores, which makes sense, obviously, but that will likely, they will at least need to consider that they should do that separately for full MVNOs, because they are separate cores. So the light MVNO, maybe they would benefit just as much as the sort of underlying MNO from a local CDN installation. But the full MVNOs obviously would need another CDN installation for themselves. And so lastly, was there a market difference between them? Obviously, yes. The light MVNO really is just the underlying carrier in terms of network performance. And the full MVNOs are different than their underlying carriers, but they're also different from each other when you're talking about the same carrier. because of that underlying infrastructure. So they essentially have 3 separate cores. I'll be happy to take any questions.
So I was wondering, do you know, so what I've heard is light MVNOs will actually have lower priority traffic on the MNOs. So if the bandwidth or spectrum is used by MNOs, they will have higher priority, and light MVNOs do not have that. So I'm a little bit surprised by the results that you have. Do you have any explanation about that?
We did capture throughput. It's not in the paper. And the light MVNO actually performed worse, sort of as expected. Across the board, MVNOs were worse than the MNOs in terms of sort of real client traffic. But in terms of like trace routes or our probes, they were very similar. So, maybe they're doing some sort of TCP balancing or
for future work, maybe look at time of the day performance.
Right, right.
Some more questions?
Do you believe that the differences that you observe in the performance of the MVNOs and MNOs affect their market share? For example, do users realize these differences and consider them when they select the provider, or are they maybe based on your prices?
I'm no economist, but I would say most people choose based on what they can afford, and MVNOs are really tempting for people. Generally, they sell well to people that don't have as many resources because they don't have these credit checks and things like that.
So the MVNOs are cheaper.
Typically, they're cheaper, and they're sort of, you're not locking at least in the U.S., you're not locking yourself into these very long contracts that MNOs typically use. So generally, MVNOs end up having sort of a poorer population of users than MNOs, which means there's sort of a class system on these networks.
Do you believe that if such kinds of performance metrics could be published, do you believe that this could affect the performance of the market positively or negatively? So if this knowledge would be offered to the public, to the users, would it be beneficial?
I'm not sure if it would have enough of a profile. The big carriers are still the big carriers, and the MVNOs are sort of the new kids on the block. So it would be hard for them to sort of change perspective.
One more question, Manuel.
Yeah. So you said you did this under 3G, so and you said there's like a limited number of gigs. Would you expect this would change under like 4G, where in a lot of cases, like an order of magnitude, more of these gateways with more kind of locality of assignment?
Yeah, with LTE, you're breaking out to IP much sooner. So, ideally, there's a lot more gateways. Ideally, you're popping up much closer to you physically, unless the carrier is actually sort of routing you to a PGW, in the middle of nowhere. So yeah, I would expect LTE is actually going to improve upon these sort of measurements.
So there's time for some more questions.
Have you noticed a change in the IP address for a specific operator for experiment during the time of day?
We didn't look at any of the time of day stuff, unfortunately.
The reason I'm asking that is the IP addresses that you're following are the SGSN addresses.
Mm-hmm.
So either they have this kind of virtualized SGSN functionality, or they have some, let's say, fixed one. So I assume that given the resources and the time of the day, the MNO chooses to offload them and
Sure.
Throw them away to a different point of their network, so they can satisfy their network needs.
Mm-hmm.
So that's the reason I'm asking for that. that somehow they, through time today, you can figure out that the spare resources are limited or not.
Yeah, that would be really interesting to look at. I would think that they're sort of shifting things around to wherever it's sort of advantageous for them. Yeah.